Now let's take a look at section 4.2 in the text, where we'll be looking at matrices and graphs. You know, the application of linear algebra, matrices, etc., to graph theory is just, well, it's huge. There's a tremendous amount of stuff you can do with it. And if you enjoy graph theory and you do find and you're okay with the linear algebra stuff, then this would maybe be a recommendation of an area of future study for you. Okay, I mean, pictures are great. I've got a graph here, a multi-graph drawn over here. I've got 5 vertices and 9 edges. Okay, and there's a lot you can do with this picture. However, how can you scan or somehow take that picture and put it in the computer and let it be analyzed? Also, if I wiggle some of these things around, okay, I mean, I can rearrange the points on this graph to where it doesn't look anything like what I started with. However, it would still be the same graph. As long as there are 2 edges connecting 1 and 2, it doesn't matter whether 1 and 2 are on the upper left or if they're somewhere else. So it'll still be the same graph. So pictures are good, but they don't necessarily tell the whole story. So we want to somehow take this information that's in this graph here and put it in some sort of format where we can do some analysis on it. Okay, now I'm going to be doing 3 or 4 definitions, and they're slightly different than the definitions in the text. The results will all be the same when we actually start working problems with them, but I found that the text had just not quite the standard sort of definitions for these. Okay, so let's start with a new idea here. For a graph having n number of vertices, okay, then the adjacency matrix A, D, J, A, C, C, N, C, Y, the adjacency matrix, it's the n by n matrix Okay, we're going to write it this way. Capital A equal, and the entries we're going to call little a sub ij. Oops, sub ij. Remember, this means the first number corresponds to the row, the second number corresponds to the column. So the entry in the ith row and the jth column is going to equal the number of edges. Oops, don't spell them that way. Don't spell it like that. Joining vertex I to vertex J. That's it. This is slightly different than the one in the book. Now, excuse me. I've got a matrix drawn down here in the lower right. The green grid is nothing except to help me keep things straight. If I don't put some sort of grid there, my alignment's going to look terrible. But for our matrix A here, every row corresponds to a vertex, and every column corresponds to a vertex. Okay, and what we're going to do is we count up the number of ways I can get from a vertex here to a vertex there. Excuse me, no, not exactly right. The number of edges that join them. Okay, so this first entry here is row 1, column 1. So how many edges join vertex 1 to vertex 1? This is supposed to be, there aren't any. Okay. How many edges join vertex 1 to vertex 2? Well, there's two, E1 and E2. How many edges join vertex 1 to vertex 3? None. How many join 1 to 4? None. 1 to 5? 1. Okay, now we go through the second row and we count the number of edges that join vertex 2 to the different vertices in the column. Okay, so this is the 2, 1 entry. How many vertices, how many edges join vertex 2 to vertex 1? There are 2 of those. 2 to 2, no, there aren't any. 2 to 3, there's 1 that goes from 2 to 3 that joins 2 and 3. 2 to 4, none. 2 to 5, 1. Okay. Third row. How many edges join vertex 3 to 1? Vertex 1. None. 3 to 2, 1. That would be edge 5. 3 to 3, yes, there is one that joins 3 to 3. Okay. 3 to 4, there's one that joins 3 and 4. And 3 to 5, there's one that joins 3 to 5. Okay. Now we do vertex 4. How many edges join vertex 4 to vertex 1? None. 4 to 2, none. 4 to 3, there's 1. There aren't any that take the start at 4 and end at 4. And there's 1 going from 4 to 5. And finally, edges from 5 to 1, joining 5 and 1, there's 1. Joining 5 and 2, there's 1. Joining 5 and 3, there's 1. 5 and 4, there's 1 edge joining 5 and 4, and there are no edges joining 5 and 5. Okay. As what's slightly different here is the book says the book does not allow multiple edges, but there's no reason to not put them in there. I don't know why they didn't. So these 2 edges from 1 to 2 show up. Okay, you count them twice. Okay, first thing to notice here, and we're just looking at ordinary graphs which are not directed. We'll handle directed graphs in a minute. Notice that the matrix the adjacency matrix of an ordinary graph. Of course, when I say ordinary, when I say graph, I mean it's not directed, is symmetric. Okay, and what I mean by that is that row I is going to equal column I, because row I are the you count up the number of edges joining vertex I to the other guys. Okay, and column I is the number of edges that join the other guys to vertex I. Okay. In other words, this one that's up here in row 1, column 5, it corresponds to the edge E3, and that corresponds to the edge down here that joins 5 and 1 together. Okay, a few more definitions here. Whoops, not quite ready with that. I should insert a blank page. Okay, definition. Okay. The degree of a vertex. Okay, this is equal to the number of edges that are incident with that vertex. Incident on that vertex is how the book puts it. Okay. So for this previous example, let me grab this. So for this guy, the degree of vertex 5 is 1, 2, 3, 4. Okay. Now, notice also that the degree of the vertex, let me scoot this out of the way here. Notice also that the degree of the vertex equals the sum of the entries in the row that corresponds to that vertex, or the column that corresponds to that vertex. In this adjacency matrix. Okay. So if we look at 5, then add up everything in column 5, that's 4. Or add up everything in row 5, that's 4 as well. Okay. Okay. The next matrix we're going to look at is what's called the incidence matrix. Okay. So suppose that we have a graph G, and it's, of course, a graph is the set of vertices and edges. It's not necessarily the picture, it's a set of points and pairs of points. Okay. So suppose G is a graph here where N is the number of vertices and M equal the number of edges. Okay. Then the incidence matrix for G is the N by M matrix capital B okay, and we're going to call its entries B sub I K from row I and column K, okay, where the entry in row I column K, it's the number of times vertex I is incident with edge K. Okay, that'll make sense after I get this here. So in other words, when we're taking a look at the incidence matrix, the rows are the vertices, and the columns correspond to the edges, E1, E2, E3, E4, E5, E6, E7, E8, and E9. I hope you can read these. Okay, so it's the number of times this vertex is incident with the edges. In other words, if we take a look at vertex 1, okay, does edge 1 touch vertex 1? Sure, one time. Vertex 1, E2 is an edge that has vertex 1, so it's 1. E3 is 1 as well. E4 does not touch, edge 4 does not touch vertex 1, so I put a 0 there. Nor does edge 5, 6, 7, 8, or 9. Okay, so none of those edges touch vertex 1. Now go to vertex 2. Now vertex 2 is an end of the edge 1 and of edge 2, not of edge 3. It is of edge 4 and edge 5, but edge 6, 7, 8, and 9 do not touch vertex 2. Okay, vertex 3. Edge 1 doesn't touch 3. Edge 2 doesn't touch 3. Edge 3 doesn't touch 3. Edge 4 doesn't touch 3. Edge 5 does. Okay. Edge 6 does. Edge 7 doesn't. Edge 8 does twice. Okay. And edge 9 does once. Okay. Vertex 4. Okay, 1, 2, and 3, 4, 5, 6. None of those touch 4. 7 does, 8 doesn't, and 9 does. And finally, vertex 5, 1 and 2 edges don't touch 5. 3 does, 4 does, 5 doesn't, 6 does, 7 does, 8 doesn't, and 9 doesn't. Okay. So one of the things we look at here the sum of each column is going to be 2, right? Because an edge corresponds to 2 vertices. Now, in the case of E8, the 2 vertices are the same, but the sum of each column is going to be 2. Okay, now we've got a theorem here. Oops, not quite ready for this. Insert another blank page. This is theorem 4.2.1. Which they refer to as the first theorem of graph theory. It says, if G is a multigraph with no loops, okay, multigraph meaning I do allow multiple edges connecting 2 vertices, but no loops. So this guy I have here, this previous example, is not a multigraph with no loops because of E8. Okay. So it's a multigraph. So if G is a multigraph with no loops and M number of edges, then the sum of the degrees of all the vertices is 2m. I said it doesn't apply to the graph we just had. Well, this is the idea here is that there are no loops. Then each edge connects 2 different vertices. And if you are counting up the degree, like if you have an edge from vertex 1 to vertex 2, okay, when you count vertex 1's degree, you've counted that edge. When you count vertex 2's degree, you've counted that edge again. So the degrees count all the edges up twice. Corollary to this is the number of odd vertices in a multigraph with no loops so you can have multiple edges but no little edges going back to the same place here is even. Okay. So the number of odd vertices you have is even. I don't know whether I should have said something back here. We're counting up the degree of a vertex. Lots of times we're only interested in whether the degree is even or not. So an even vertex is what I mean by even degree, and an odd vertex is a vertex of odd degree. Okay. So many times in the problems we're working with, it doesn't matter so much the degree that vertex has degree 4, vertex 5 has degree 4, but that vertex 5 has an even degree. Okay, so let me get back. Sorry, I should have said that a while ago. The number of odd vertices in a multigraph with no loops is even. And the proof goes something like this. Okay, so we might have multiple edges joining two vertices, but we don't have any loops. Let's let R be this number we're after. Okay. Now, let's let P equal the sum of degrees of the odd vertices. So when we add up all the degrees of the odd vertices, that's going to be P, and let's let Q equal the sum of the degrees of the even vertices. Okay. Now, I have a multigraph with no loops, so I can use a previous theorem. So the total degrees is 2 times m That's 2 times the number of edges, and that's going to be P plus Q. Okay. Okay, well, I don't really care what M is. I'm not trying to count up how many edges we have. I just know that P plus Q is even. Now, let's go back to Q here. Q is the sum of the degrees of the even vertices. So when you add up all these are a bunch of even numbers then. The degrees are all even. So Q must be even. So I have P plus even is even. Well, now, what does that tell me about P? Then P must be even minus even. So, and P then must be even. Okay. All right, now what is P? P is the sum of the degrees of the odd vertices. So every vertex here has an odd number, has an odd degree. So P we take the first odd vertex plus the second one, so you're adding up the degrees of all of these. Okay. So P is the sum of a bunch of odd numbers. How many odd numbers can you have? Well, we're using a little bit of number theory here and getting a little bit sloppy, but remember odd plus odd is even. So the only way you're going to get an odd number when you add up odd numbers is to have an odd number of odd numbers. So we must have, excuse me, if this is even, We must have an even number of odd numbers, so R must be even. Because that's how many odd vertices you have. Okay. Now let's talk a little bit about directed graphs here. Here I have taken the original graph and put some arrows on it so that it's now a digraph. Okay. And the adjacency matrix is defined a little bit differently here. So for a digraph for an adjacency matrix, the adjacency matrix again, it's the n by n matrix where A sub ij, a particular entry in the row ij column, this is the number of edges from vertex I to vertex j. Okay, so we have a direction here, not the number of edges that connect these two, but the number of edges from one to another. So how many edges are there from 1 to 1? None. From 1 to 2, there's 1. From 1 to 3, no edge goes from 1 to 3. From 1 to 4, no. From 1 to 5, 1. Okay. Okay, so now we're counting up edges leading out of 2. So from 2 to 1, there's 1. There is no edge from 2 to 2. From 2 to 3, there's not an edge. There's one that connects 2 and 3, but it goes from 3 to 2. From 2 to 4, there is no edge. From 2 to 5, there is one edge. From 3 to 1, there's no edge. From 3 to 2, there is one edge. That's E5. Okay. From 3 to 3, there is one edge. 3 to 4, no edge starts at 3 and goes to 4. And no edge starts at 3 and goes to 5. Okay, 4. 4 to 1, nope. 4 to 2, nope. 4 to 3, yes, there is an edge that goes from 4 to 3. 4 to 4, no. 4 to 5, no. And finally, edge 5, is there an edge going from 5 to 1? No. From 5 to 2? No. From 5 to 3, yes, there's one of those. From 5 to 4, yes, there's one. And from 5 to 5, no, there is none. So this is the adjacency matrix for a directed graph here. Okay, now we'll talk about degree things for a digraph. For a digraph, for a directed graph, the out degree of a vertex okay, that's the numbers of edges from. Okay, and the end degree it's the number of edges into a vertex. Okay. So for these, we have here so vertex 1, 2, 3, 4, 5. Make a little table here. Okay. Okay. Those going out of 1, there are 2. The out degree of 1 is 2. The end degree, there's one vertex going into 1. Okay. For vertex 2, the out degree is 2 because E1 and E4. The end degree is 2 because E2 and E5. Vertex 3, okay, the out degree is 2 because of E5 and E8. In other words, it's the how many edges start with 3, okay, and the end degree is 3 because E6, E9, and E8 both end in 3. For vertex 4, the out degree is 1, the end degree is 1. And for vertex 5, the out degree is 2. We're talking about edge 6 and 7. And the end degree is 2. We're talking about edges 3 and 4. Now, looking at these and looking back at this matrix here, the out degree of a vertex is the sum of a row for that vertex, and the end degree is the sum of the columns corresponding to that vertex. Okay, now let's talk about the incidence matrix when it comes to directed graph. Now, one of the things we're going to have to do on this one is I've got to change this a little bit. If we're doing an incidence matrix for a directed graph, we need no loops. Okay, so I erased the vertex 9 here. And what I should have done is erased one of these columns, but I didn't. We'll just leave it blank here. Okay, so the incidence matrix here, we're going to call it capital B. And it will be an entry in capital B will come from row I and column K here. And B sub I K is going to be -1 if edge K starts at vertex I it's going to be +1 if edge K ends at vertex I, and it's going to be 0 otherwise. Okay, so let me scoot this guy down a little bit. Okay, so again, this is going to be my matrix B, and here, these are the vertices. Each row, the edges are E1, E2, E3, E4, E5, E6, E7. Now I erased E8, E9, and this column shouldn't even be there. Okay. Okay, so we look at what goes into and out of. All right, vertex 1. Edge 1 goes into vertex 1, so that's a +1. It ends at that. Edge 2 goes out of 1. It starts at vertex 1, so that's -1. Edge 3 also starts at 1, that's -1, so it's going out. Edge 4 doesn't have a thing to do with 1, as does 5, 6, 7, and 9. Vertex 2. Okay. Vertex 2, edge 1 goes out of 2, so that's a -1. Edge 2 goes into 2. Edge 3 doesn't have anything to do with 2. Edge 4 goes out of 2. Edge 5 goes into 2. And 6, 7, and 9 don't touch 2 in any way. Vertex 3 doesn't have a thing to do with edge 1, 2, 3, and 4. Okay, they don't touch 3. Now, edge 5 goes out of 3. Edge 6 goes into. Edge 7 doesn't do anything, and edge 9 goes into. For 4, okay, edge 4 doesn't have anything to do with any of these guys until you get down to 7 and 9. Okay, 7 goes into 4, and 9 goes out of 4. Okay, and 5, okay, 1 and 2 don't have anything to do with vertex 5. 3 goes into, 4 goes into, 5 doesn't do anything with vertex 5. 6 goes out of, 7 goes out of, and 9 doesn't do anything there. So this is the incidence matrix of this directed graph B. Now, something to note here, if you add up a row, that's the in degree minus the out degree. Okay. So if we added up row 1, we'd have 1 minus 1 is 0, minus 1, you'd have a negative 1. So what that means is there's one more thing leading out than leading in. Okay. And also the sum of a column should be 0. Okay, because every edge goes from one place to another. And that's what each column corresponds to an edge. Okay. All right, last, I'd like to work a problem from the exercises. This is 415, page 137. It's a pretty simple problem here. Okay, we have a new definition here. A graph where all the vertices have the same degree is called a regular graph of degree R in this case. Okay, now in part A, we're asked to construct a simple regular graph. So simple meaning no loops, no multiple edges. A simple regular graph of degree 1 is not complete. Now a complete graph is certainly regular. Because every vertex is connected to every other vertex. Okay. And so if you have n number of vertices, then the degree of every single vertex is going to be n minus 1 because it's going to be connected to all the other ones. Okay, but what we're looking at here is let's construct a simple regular graph of degree 1 that's not complete. So I don't want a complete graph, which is simple and regular. Okay, these are really pretty simple. You might have a little problem if you insist on your graphs being all connected up. Degree 1 just means that every vertex has to have an arc going from it. Okay, and so there's one. Actually, get even simpler than that. You can just take the top two. Okay, two separate pieces in this case. Vertex 1 is degree 1, as to are 2, 3, and 4. It's simple. There's no multiple edges, no loops. So there you go. Okay. B, a simple regular graph of degree 2 that's not complete. Take this guy we just did and do this. Okay, there's a simple graph of degree 2 that's not complete. If it was complete, I would have something going from 3 to 2 and something going from 1 to 4, but it wouldn't be degree 2 anymore. Okay, now finally, part C is if G is a regular graph of degree R and G has n number of vertices, find the number of edges. Okay. So n number of vertices, each with degree r. So what happens when you add all of these up? You take r plus dot 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 plus r of them, n times r, and this is the total number, the total of all degrees. Okay, now this is I'm assuming this is a graph with no loops, which means we can use theorem 4.21. If G is a multigraph with no loops and m number of edges, the sum of the degrees is all 2m. Okay. So if no loops, then the sum of all the degrees, it should be a sigma, which didn't, equals 2 times the number of edges. Okay, and we just said that was n times r, so the number of edges, n times r over 2. Okay, pretty simple problem. Well, there you have a brief introduction to graph theory and how you can use matrices. We'll do some other matrices as we go along in here, and we'll start using the adjacency matrix. It's a very useful sort of thing here. I may give you a few examples of some other matrices that aren't in the book. I haven't decided yet, but there are more than just the two we've looked at. And you should be able to work the problems in this section pretty easily.